All right, thank you. So sort of did the usual thing when I was asked to send in a title, an abstract, which I just took whatever I was working on most recently and said, hey, this is what I feel like talking about. Then I sort of remember the conferences have themes and maybe I make sure that it's related to what the conference is about. So this looks like it's not about computability or combinatorics, but it is. History is really about how to take some things that don't look like that and make them into something that looks more computable. All right, so a little bit of model theory. So a theory admits quantifier elimination if every formula is equivalent to a quantifier-free formula use it in the theory. So classic examples are things like the dense linear order without endpoints. That is the theory of the rationals is just an order, right? If you want to know if something is true, if there exists some configuration extending your points, well, you just need to know about the configuration of the points, which points are less than which other points. The random graph, say limits in general tend to admit quantifier elimination, algorithmically closed fields, etc. And many well-known theories of quantifier elimination. Maybe the best known non-example is Pressburger arithmetic, right? So this is arithmetic in the language with just less than, zero successor, and plus. Because maybe the best known example of the theory without quantifier elimination is Peano arithmetic. But Pressburger arithmetic is sort of a more informative example. So first of all, the reason it doesn't admit quantifier elimination is because with just addition, you can write down a formula that says x is even, right? The formula, there exists a y, so that y plus y equals x is true exactly when x is even, but there's no quantifier-free formula that expresses that x is even. And it's an interesting example because it turns out this is more or less the only obstacle to quantifier elimination. So, the result that many of you have seen proven is that if you add unary predicates that express divisible by n for each natural number, then the theory admits quantifier elimination. And so most often when we talk about quantifier elimination, we really want results like what we have about Pressburger. The idea is if you have quantifier elimination for a theory, you sort of understand the definable sets very well, because the definable sets are all quantifier free. That means they're Boolean combinations of the quantifier of atomic formulas. So if you know what the atomic formulas look like, you know more or less what the definable sets look like. And often the goal is to take a theory and maybe not prove quantifier elimination just for that theory, but to extend the language by enough extra symbols so that then we can prove quantifier elimination. Right? At that point, you can say that in some sense we understand the theory in a certain way because we've found the additional formulas you need to add to get quantifier elimination. All right. So all the examples on the previous slide, all those quantifier elimination results, these are classical results from largely the first half of the 20th century. And the original proofs are all algorithmic, right? So if you have quantifier elimination, you could hope to have an algorithm that takes an arbitrary formula and transforms it into the equivalent quantifier. That's the naive thing you'd think that people mean by quantifier elimination. Give it a formula, you have some way to produce the quantifier free equivalence. But most modern quantifier elimination proofs are not proven. So model theorists developed a set of tools that are sometimes called saturated embedding tests, because they are about embeddings of saturated models of theory that let them prove quantifier elimination by doing model theoretic stuff with large models of the theory. And these tools are very well suited to the things that model theorists like to do, and they're very effective at proving quantifier elimination results, but they don't look out. So sort of an example of what these tests look like, and I'm citing this directly to Marker's textbook, just to point out this is a very standard technique that you can find kind of in standard textbooks on model theory. This is a typical example of what a saturated embedding test looks like. So a theory has quantifier elimination so the picture really looks like this. So I have a model M and I have a big model N, which is saturated, sufficiently saturated, and they overlap on a set A. Right. I phrase it here as it's often phrased, there's a homomorphism, but of course, well, you could just pretend that you could always just replace the elements A with their image and make them the same. So imagine you have models that overlap on the set A, which is not typically a model of the theory. Right? So it's typically not going to satisfy the theory, it's missing elements, but they just have some common stuff in their domain. And the theorem says that if you have this configuration and N is sufficiently saturated, you can just move all of M over and you can find an isomorphic copy of M inside M. And if you can do that, then the theory has quantifier relation. And that's actually an equivalence. It's not, well, as we'll see, it's not that hard a theorem. As I sort of learned very quickly when I started looking at these results, model theorists tend not, it's not like there's this theorem and model theorists just use this all the time. In fact, basically every quantifier elimination result uses some other minor variation of this theorem, and they just keep tweaking it for whatever they need. So here's a version that is a little more convenient to work with, and is what we'll talk about. So we have the same, basically the same picture. We have a model M, we have a model N, N only needs to be omega saturated now. It's still a big model, but it's not as big. The set A is actually finite, and I only have to promise that I'm going to map one element from M to N. So this is actually almost as good as the previous results, because basically, if you can map one element, well, then you can map another element and another and another. So actually, you can sort of get from something like this to the previous result without a ton of. Okay. I'll actually talk about the proof of this. It's not a long proof, and it illustrates what's going on. So, first of all, right, standard fact, if we want to prove quantifier elimination, it suffices to show that we can eliminate one quantifier. Because then if you have a formula with lots of quantifiers, well, you eliminate the innermost quantifiers, you replace them with quantifier-free things, and now you have one less quantifier depth, and you iterate until there's no quantifiers. So it suffices to show that if we have just a formula of the form, there exists an x phi of xy, where phi itself is quantifier-free, then this existential is equivalent to quantifier-free. All right, so I have this quantifier-free formula given to me. I want to show that I can eliminate the quantifier. I'm going to add some constant symbols for the y values. So I'm going to give them names that are in my language. And then I'm going to look at the theory that's my theory T that I'm interested in, together with the negation of the existential, the universal formula for all x, b does not hold of x with the constant symbols d. All right, so if that's inconsistent, then the universal formula is equivalent to bottom, and the existential formula is therefore equivalent to top. As an aside, this is one of the reasons you should have bottom, like your conception of first order logic should include bottom as a connective. Because actually, if you don't have bottom as a connective, this theory gets wonky and you have to start adding, like, as long as the language has at least one constant symbol conditions to these tests, and you shouldn't need those. So you really actually need bottom in your language if you don't want to deal with some technicalities. Okay, putting that aside. So if this is inconsistent, then we're done. We have an easy quantifier-free equivalent. Otherwise, it's consistent. Consistent theories have omega saturated models. So that's where our model N is going to go. Let sigma be the true quantifier-free sentences from N. Our goal is to show that sigma implies the universal form. Right? Because if that happens, right, then we do a compactness arc. If sigma implies the universal, then a finite subset of sigma implies the universal, and then the conjunction of those formulas is a single quantifier-free formula. It's implied by the universal, it implies the universal, so it's equivalent. So the negation of that conjunction will be the quantifier-free formula equivalent to the existential that we're interested Our goal is to prove that T union sigma is, to prove that sigma implies the universal. Then we argue by contradiction. If it doesn't imply the universal, then T together with sigma, together with the existential, is consistent. Well, let's take a model of it. We call it M. These two models share elements D and they agree on sigma. So in particular, they agree on the quantifier-free facts about D. So they can really sort of share these elements D. And then, well, our assumption is that I can take the element A, which is in M, and I can map it to M. Oh, well, wait a minute. A satisfies phi. Phi of A D holds because that's our assumption on M. But nothing in N can satisfy that because that's our assumption about N. That's our contradiction. Therefore, M doesn't exist. Therefore, T union sigma union the existential is inconsistent. And then you work back through the chain of implications and we get the inconsistency. So that's the proof. It's not long. Mostly, at least if you're like me, it's just confusing keeping track of which model satisfies which formulas. And it's otherwise not a deep theorem. Relatedly, there can't be that much content in it. It can't be doing much of the work. Most of the work is then using this theorem and using your understanding of models to prove that this premise holds. All right. These get used a lot. There are many results in literature that use this method to prove quantifier elimination. They're used mostly for the sorts of theories that model theorists tend to be interested in, which means lots of extensions of algebraically closed fields, used for differentially closed fields, for algebraically closed value fields, for differentially closed value fields, et cetera, et cetera. Also, we'll see an example at the end of the talk. A lot of theories that look like the reals, or more generally like O-minimal structures, plus some additional sets. So you take something like the reals and you add like, I have a predicate that tells me which real numbers are of the form 2 to the z for an integer z. Theories like this. I'll mention specifically, so there was this book, maybe 6 to 8 years ago by Aschenbrenner, Van Dries, and Van der Hoeven, this like 800-page tome on trans series. It won like the book prize from the ASL. It was this sort of big results about big sort of summing up of a lot of developments in the model theory of these sort of infinite series. And actually the culminating result, like the last section of the book, and like they say, like the point of this book is to prove quantifier elimination for this theory of trans series. And they build up all this model theory of these series to prove quantifier elimination. And they actually, I went and checked just out of curiosity, and they use exactly this version of the saturated elimination test. So these are productive methods for proving quantifier elimination. In some cases, people have subsequently found algorithms. So people have come up with new proofs of quantifier elimination that actually give algorithms. But for many of these examples, there aren't known algorithm proofs. So a little bit of proof theory, computability theory stuff. If you have, when T is a computable theory, or computably numerable theory even, which all the theories we're talking about are, the statement that your theory admits quantifier elimination is encoded by a pi02 sentence. That is, it expresses that a particular computable function is the total computable function. Because what it's saying is that for every code for a formula, there exists a code for a quantifier-free formula and a code for a deduction that these two formulas are equivalent. And right, so there exists this total recursive function, this total computable function, where you just like blindly search for the correct thing. And your proof of quantifier elimination tells you, okay, this function always terminates. You don't know how long it's going to take, but you promise this function always terminates. And there are these abstract results from proof theory that say, if you have not just the fact that a pi2 sentence is true, if you have a proof of that, then that proof has to contain an output. And this is just generally true, that if you prove a pi2 statement in the language of arithmetic, if you prove that a computable function is total, you have to have given an output somewhere. So if that 800-page book about trans series had been written in the form of formal deductions and then it would be totally straightforward formality to just apply general results from proof theory to obtain an algorithm. Of course, no one writes anything as formal deductions in proof theory or any other system, right? People write mathematics in English using normal arguments. And so one of the central goals of proof mining is to take these meta theorems and figure out how to apply them in practice to mathematics as it's actually done, which means, in ordinary mathematics goes beyond reasoning that you can state in arithmetic, you can state in the language of arithmetic. So there's been a lot of work extending these results to things like results in analysis, so things where you have to talk about analytic spaces and figuring out how to make sense of those. There's been a bunch of work by me and others on how do you take proofs that use ultra products or non-standard analysis and extract algorithms from those. So the work I want to talk about here is part of a newer project trying to figure out how to make sense of uncountable cardinals. Right. So what bothered me about these results is these omega saturated models, they're uncountable. And you shouldn't really need to know anything at all. You shouldn't need to talk about uncountable sets to prove that algorithms are total. Like that shouldn't really be telling about that. So the goal was to figure out how do we extend these proof mining methods, these saturated tests. So we have to replace this discussion about models and uncountable models with something that's fundamentally not necessarily computable, but computational. Something we can express in arithmetic, something we make sense of in sort of computational ways. So how do we replace the notion of a model, especially an uncountable model, with something fundamentally computational? So one approach is, in fact, something like what we just saw in the previous talk about computable rings. So you could say that, what is a computable model? Well, it's a model, its universe is the natural numbers. And and you have an algorithm that tells you what facts are true about it, or maybe tells you what quantifier-free facts are true about it. And this is a bit too narrow. For example, the completeness theorem doesn't hold for this. Right? So our basic example of the sort of thing we want to model of is we're given a set of sentences that's consistent and we'd like a model. And there are sets of sentences that are no computable model. The next thing we might try, which is good enough for us, is like a computable model, but it's just allowed to be wrong sometimes. So it's just a computable function that outputs sets of sentences, it outputs facts about our model, but sometimes it's wrong. But when it's wrong, it has to eventually notice that it's wrong and get it right later. So what I'm describing is a limit computation of a model, or a delta 2 model. And this is exactly what we need. So for my purposes, here's what I'll say. So an approximation to a model is a function h, which will always be computable. For each n, h of n is going to be a finite set of sentences. It's going to be the language ln, so that's whatever our language is, plus constant symbols for the natural numbers. Right, so our universe will be the natural numbers, and we'll actually name the natural numbers. So h of n will be a set of sentences about it. And the most important property is the second one. It has to eventually, converge. Right, so for every phi, we might for a while say phi is true, right? H of n is supposed to be the set of true sentences. So we output phi for a while, and we go, oops, that leads us down a bad path. Okay, not. And we might change our mind again, but eventually we get it right. Every axiom should be, that should say H of n there. Every axiom of T should eventually show up. So we should actually be a model of T and not some other theory. And we should be closed under consequence. I've left out, we should also, if you think that something exists, you should eventually say and name an element that satisfies that. Left that out of those conditions. So if you do that, then you can take the limits, right? The limit of h of n exists, and it's a set of formulas. And if you satisfy all these properties, then that limit is actually the theory of a model, right? It's going to be a complete theory. I'm not assuming it's consistent because it's just convenient to allow inconsistent. It's convenient to allow non-models in this story. It's convenient to have things that say this is an approximation of a model, and the only way it goes wrong is if it turns out to be inconsistent. But it's allowed to turn out to be inconsistent. So just this sort of natural way to produce these looks something like this. So I have this, so I will have a set of formulas and I want to produce a computable approximation to a model of it. So T union sigma union exists in X phi of AD is the stuff I want to definitely be true, and then I just want to produce a model of it. I can just kind of do the naive thing, which looks like this. So first, I pick an enumeration of all the formulas. And then I say H of n is going to decide the first n formulas. Right? So H of n will look at the formulas psi1 through psi n, and for each of them it will say either psi I is true or not psi I is true, or both, but at least one of them is true. And the way we defined H of n is, okay, so T and sigma that exists in X phi sort of get top priority, right? Those are things we definitely have to satisfy. So if those are true, we definitely put them in H of n. Sigma might be a computably enumerable set. So what I really mean is I like check for n steps to see if something shows up in sigma. And if it does, I put it in. But T union sigma union exists in X phi is probably incomplete. So I have a bunch of formulas I haven't decided. And I just need like a coherent way to decide them. So I look at like psi1. And if psi1 hasn't been decided, I look for n steps for a proof that psi1, for a proof of not psi. For something that says I have to make psi1 false. And if I find that, of course I make not psi1 false. And if I don't find that, I put in psi1. And now I've committed to psi1 and I look at psi2. And again, I search for n steps for a proof of not psi2. Now I'm allowed to use psi1. And if I prove not psi2, then not psi2 goes in H. And if I don't prove it, then I just decide, okay, psi2 is safe. And I put psi2. And I just decide all the undecided formulas one by one this way. And at some later stage, I might discover a proof that was too long for me to find before. So this is when I change my mind. Right? Earlier I said psi2 was true, then later I discovered that was inconsistent, so I changed my mind. And I put not psi to it. But then even later I discovered that actually psi1 was inconsistent. So I flipped psi1 to not psi1, and now I might put psi2 back to psi2 again. Because my old proof of an inconsistency relied on psi1, and now I've learned that it was psi1 that was the problem. But the point is this eventually converges. Eventually I settle on psi1, and then once I've settled on psi1, I settle on psi2, and so on. So this converge. So I do get convergence. I eventually converge on a model. Okay. Yeah.
Can I ask how do you ensure the witnessing property you mentioned?
You like designate some elements to serve as witness. You like pick a computable scolumization and you say, if so, like I decide like 7 is going, if exists in X psi is true, then 7 is a witness to that. And if it's not true, I don't care what happens. And so then if it looks like exists in X psi is true, then okay, I have a commitment about what happens with 7. Yeah, it is sort of annoyingly hard to write this up correctly and coherently, and it's not that deep an idea. It's just somehow getting the technicalities right. That's really tedious. It's only going to get worse in 2 slides. Let's talk about saturated. What on earth is a saturated model in this context? Because saturated models should be uncountable. So there's a pattern that when we try to take statements about uncountable objects and sort of push them down to computable-ish things, that they often sort of turn into higher order objects. What I mean by that is something like this. So saying that a set is uncountable is saying there is no surjection from the natural numbers to this set. And it turns out that sometimes when you want to like computational analog of this, what you end up with is saying, instead of looking at a function lowercase f from the natural numbers to a fixed set S that's presumably uncountable, which doesn't make sense in a computable setting, I look at these like dynamic objects where I have a functional f and then a function s, and s now turns this functional f into a set, and then f is allowed to look at that set and produce a function. And what I'm kind of saying is that like s wins. F is trying to make a surjection, and s is trying to not be surjected upon. And you can sort of hope that s wins is somehow saying like these constructions are succeeding at being s sort of being uncountable-ish, right? It's not surjected upon. This obviously depends a lot on what the other restrictions on that is. So that's what we're going to do here. So a saturated embedding, or an embedding of a model into a saturated model is going to look like this. I have a function rho, which is going to try to be my saturated model. I have a function h that's just going to be a normal model. And there's an interplay between them. So they're both approximations of models, but when rho outputs facts about big A, about the common domain, H has to accept. So rho outputs, rho announces, hey, I've decided that this thing is true about the quantifier free part, and H has to go, okay, well, you know what that looks like, so I've got to accept that. But then H outputs things about this extra element, and rho has to accept that. Right? So H says, so rho is saying, I'm building part of a model, and H is saying, okay, but here's one extra element I want you to include. So if you imagine that rho is outputting like a countable subset of a saturated model, this is a very reasonable thing to ask for. Rho starts outputting this countable subset, and H says, I've got one more element I want you to include. And then rho says, okay, like I'm a subset of a saturated model. There is an element out here that looks like this guy you want me to include. So sure, I can include one more element that you need. And I sort of think of them as like fighting over which, at least in the context we're going to use this, they're fighting over which one has to be inconsistent. Because they're actually constructing models that are incompatible with each other. And they're trying to force each other to be inconsistent or non-congruent, right? Because there's this back and forth between them. So they have to worry about convergence. Okay. So the claim is you have a saturated embedding test that looks just like the model theoretic one, kind of rephrasing this thing. So if you have an H in a row with the kind of interrelation that I described in the previous slide, rho had better converge on these statements, right? If rho just keeps like changing its mind, then things go wrong. But rho commits to at least on these statements eventually converging. Then if H also converges and is consistent, rho is consistent. So in other words, H can't force rho to be inconsistent, other than by being inconsistent itself. So if this happens, actually we have quantifier elimination. And the reason is, you just copy over the model theoretic proof. So rho is the sort of natural approximation of a model of T together with the universal statement. It just starts outputting consequences of T union the universal, and it just makes whatever decisions it feels like making about D, and it makes sure to converge on these, which is the natural thing it does. H sees facts showing up about D and has to accept those, and then makes up stuff about A and copies them over. Rho has to be inconsistent, because H is forcing it to out, right? H is forcing phi of AD to hold, and rho is committed to phi of AD not holding, so rho is inconsistent. Our assumption is that that forces the inconsistency back to H, and that's actually enough to tell us that H is inconsistent, and we get the quantifier equivalent. So all I've really done so far is take a perfectly nice looking model theoretic test and rephrase it as something much more confusing and complicated. The reason for this, which is I like things complicated, but also because this is an arithmetic statement, right? Like there's no uncountable cardinals. There's actually no full models. This is an arithmetic statement, right? The statement that we can have these two functions, they're computable functions, they're encoded by Turing machines, they're encoded by codes for Turing machines. The statement, if this one converges, then that one converges, and if this one's consistent, that one is consistent. These are arithmetic statements. So we've actually turned this into an arithmetic argument. And then, well, from my perspective, then we can prove them. Then we can look at it for algorithm. So really what this is saying is this is giving us a lens to go look at model theory and reframe the model theory as this indirect way of talking about computations, and then we can pull algorithms out. So what I want to do with the second half of the talk is just kind of preview a little bit like that this actually works, that even though this is, not a like deep reframing of what's going on, but it's enough of a reframing that we can just go look at model theoretic proofs of quantifier elimination and start reading off algorithms. So I want to mostly illustrate this by talking about quantifier elimination for algebraically closed fields with characteristic 0. So there's a well-known explicit algorithm for quantifier elimination. Unsurprisingly, it is in fact exactly the thing you would get, and we will get as we read it off from the model theoretic proof. Like they're really the same proof of quantifier elimination. They're giving the same algorithm. But I'm choosing this example because there's a nice, fairly short model theoretic proof that quantifier elimination holds using the saturated embedding test that sort of does a good job of illustrating what this method looks like. So this is the statement that the saturated embedding test works for algebraically closed fields. So the theorem says, I'm just going to keep like pointing at the same picture. The same picture we keep drawing. If I have this situation, M is an algebraically closed field of characteristic 0, N is an omega saturated algebraically closed field of characteristic 0. I have a finite subset. I have one additional element in M. I can map this element from M over to some element in M. All right, so how do we prove that? So the proof goes by cases. The cases could look like this. First of all, these elements, they generate a subfield, right? You could add these out. This is finite, so like it's not the full field, right? They generate elements. The field generated by these elements consists of things that look like this. So there are ratios. So the thing you can do, right? You can add elements together. It's not quite right. The AIs are products of elements from A, not just elements from A. That doesn't change much. So you basically take polynomial combinations of the things you already have. You can multiply them by rational coefficients because you can express all rational numbers in the language of fields, and you can take ratios of these. And that's the entire field generated by these elements. So if A is equal to some ratio of this kind, well, that tells you exactly what you have to map it to. You have to map it to the same thing. And you can do that because the properties of this element are just determined by the things we spoke about. Okay. All right. So the second case, we might not be in the field generated by these elements, but we might be in the algebraically closed field generated by these elements, right? Which means that this element A that we're interested in satisfies a polynomial over, well, not these elements, but over the field generated by these elements, right? Which means we have a polynomial whose coefficients are ratios of the kind from the previous slide, so that A is a root of the polynomial. And then you say you choose P to have minimal degree, and then you take the image of A to be anything of minimal, any root of the same polynomial, or image of that polynomial. This is actually the most complicated step mathematically. Like, it takes some non-trivial field theory. It's like undergraduate field theory. Like, it's not really deep, but actually, when you start trying to turn it into an algorithm, you discover there's a lot of stuff about like polynomial division going on to establish like why is it that I can, that every root of the minimal polynomial over here looks the same and satisfies the same formula, and verify that holds. That takes some non-trivial work. But we'll just accept that it's true for the purpose of this. So the remaining case, right, is that doesn't happen. So our element in M is not in the algebraic closure of the field generated by these elements, which means it doesn't satisfy any polynomials, which means it's transcendental, and all transcendental elements look the same. So you can just take anything over here. How do you know that there's an element that's transcendental over the field generated by these? Well, that's what you use omega saturation for, to guarantee you have something to move it to. So that's the model theoretic proof. And the claim is that we can sort of read off an algorithm, so that there is actually an algorithm embedded in this argument. And this goes something like this. So how are we going to read off an algorithm? So I'm looking at a quantifier-free statement phi of xy. I want to take the existential, there exists an x, phi of xy, and I want to find a quantifier-free equivalence. And I have these models, these approximations to models H and rho, and H is trying to make the existential consistent, and rho is trying to make it inconsistent. And I again like to sort of think about them as like they're in a dialogue, and they're competing over whether phi of AD is going to be true. And so it turns out the model theoretic argument, so that schema we just saw where you sort of start with, you break it into cases and you say, well, either either A is expressed by an equation, is basically a term generated by these, or if it's not that, it's at least controlled by a polynomial, or if it's not that, it's something far out. That scheme happens a lot, where you kind of start with things that are close by and you work your way out to things that are far away. Turns out, for these arguments, it's kind of useful to think in the opposite direction. To start by saying, what if A is way, way out there? And we'll rule that out, and rho is going to force A to get closer and closer to D until we run out of cases. Right, so imagine we're trying to build these models, and rho is making decisions of, so rho is trying to make phi of AD false. And to do that, it gets to ask questions to H about A and D, about like quantifier-free formulas. So in the language of algebraically closed fields, the only quantifier-free formulas are basically of the form P of AD equals 0. Right there, you can always rearrange so that they look like this. So you can assume that all the quantifier-free formulas are these polynomials. And so that means phi is a Boolean combination of these. Is a Boolean combination of formulas. Right? So some formulas are false, some formulas are true, and some complicated Boolean combination. So rho goes to H and says, here are some polynomials I'm interested in. Are they true of AD? And H is then allowed to ask questions about D. Right? So for example, rho says, hey, is this polynomial true? And let's say H is trying to make A transcendental. So A wants to say no to every polynomial. But there's a catch, which is the polynomial could be trivial, right? Because a polynomial has the form, polynomial looks like that, where the CIs are terms in D. The CIs could all be 0. In which case H had better not answer that this is false. Right, so Rho says, do you think this polynomial is true? H says, what about the C's? Is one of the C's, is one of these coefficients non-zero? And if Rho answers all the coefficients are zero, then H says, well, then I think the polynomial is zero. Thanks for asking. And then if Rho is trying to, force H to make decisions. So typically Rho might say, yeah, so one of them is non-zero. I guess H could then ask which one, but H doesn't actually need to, right? H just says, okay, one of them is non-zero, great. Then no, I don't satisfy that. My element is transcendental. My element is going to be transcendental. Okay. Well, what happens? So why was the model theory done once we knew the element was transcendental? Well, the model theory was done because all transcendental elements look the same. What does that really mean? That means every formula, right? If I have any, let's say any quantifier pre-formula, if A is transcendental over D, that just determines whether phi is true. All right. So if we want to get something more concrete about that, we have to ask, like, well, why? Like, why specifically? Well, the answer is this is just polynomials. All the polynomials are non-zero. So you just go through and you replace every polynomial in this formula with, what you just say, well, every polynomial, every formula P of AD equals 0, you replace it with bottom. And now I have a formula that doesn't depend on A. So it's determined. So in terms of our gain between Rho and H, what happens is Rho asks H about every polynomial appearing in phi. For each of them, H asks a question back. And if they're all, and once they're all established to be non-zero, we actually know whether phi is true. So what that turns into is a statement like this, right? The transcendental case is telling us, look, given phi, we can find this finite list of polynomials. It's actually more or less the polynomials that appear in phi. And if these are all non-zero, we have a quantifier free equivalence. And that's the transcendental case. And then, look, if this doesn't happen, there's only finitely many of these. So then we look at finitely many cases of the form you look at finitely many cases that look like this. So then we look at the polynomial case. And this is, again, like by far the longest case. So I'm not going to go into details because, again, then you go, why is it that if A is algebraic, then I know what to do? And the answer goes into all this stuff about minimal polynomials. Note that this might not be a minimal polynomial. Okay, actually worse, whether this is a minimal polynomial depends on the D. Depends on facts about the D. So you have to write a long thing about how the D's control polynomial division to establish whether it's minimal. Okay, this is the spirit of what happens. That you follow that you turn the model theoretic argument into an algorithm, and you discover that all the calculations going on the model theory side, they're really telling you about some formulas that have to be true. I want to point out there's a very typical thing that's happening here. So in the model theory, we had this division into the case where A was transcendental, which is a pi1 case, right? It's saying there's this infinite sequence of polynomials and they're all non-zero. And then there's a sigma 1 case, which is the algebraic case. And this is very typically what happens in mathematical arguments. That you discover you have this division into a pi1 versus sigma 1 case. And the problem is this isn't computable. So what consistently happens is that you find a different division. that goes like this. So you have to say, look, in order to do something computable, I have to divide into either a case where actually there's like not just there's a witness, not just there's a polynomial that's satisfied, but it's like a small polynomial. In this case, it's literally one of the polynomials appearing in our form. In general, life is harder than that. But you say, look, if there aren't, either there's a small polynomial, and then I do the sigma 1 thing, or there's not a small polynomial, and then I can act like it's transcendental. It might not really be transcendental, but it's transcendental enough. It acts enough like it's transcendental that I can pretend it's transcendental. I can do what the transcendental case will. And this is sort of where the hard part, where the proof binding machinery really comes to play. It's kind of figuring out how do you take these non-computable case splits and turn them into things that are computable. This gets much harder when these are not sigma 1 versus pi 1, but like sigma 3 versus pi 3, and then figuring out how to redivide it computably against each other. So one more example that is not, well, this is actually pointing towards new stuff. An example so the first example I was looking at to actually sort of apply this method to get something new is this result. So Vendries and Gnaden were looking at fields where there's this additional subgroup that gets named by a predicate, and they need it to be small. The relevant notion of smallness is this. So here's the story. So we're looking at, actually they don't need to assume it's characteristic 0. Let's just assume it's characteristic 0. We have a multiplicative subgroup of the field. Let me maybe tell you, like, these are the examples they're thinking of things like 2 to the z, 2 to the q, 2 to the z times 3 to the z. So things that look like this. They're multiplicative, they're described in some nice way. Powers of 2, powers of 3, stuff like this. They're multiplicative subgroups. And the way, and this property says they don't have many additive relationships. Right, because this is a way of saying they're small. If there were lots and lots of elements, you'd expect them to start satisfying linear equations. And this is saying actually they don't satisfy very many. So each linear equation, so I want to say each linear equation has only finite many solutions. There's a problem with that, which is it could be that there's a subset which adds up to 0, which has a solution to the homogeneous equation, and then you could take this and multiply it by a constant. And you multiply by any constant, and you get infinitely many solutions. Okay, so you have to say that's the only way you get lots of solutions, is because you have a solution for homogeneous equations. So you have only finitely many non-degenerate solutions. And so this is really a way of saying you have as few linear relationships within this group as you could hope to have. And it's satisfied by all these examples. And their result looks like this. So this is the real closed version of it. You start with you take a dense subset of the positive real numbers, like dense, so not 2 to the z, but like 2 to the q, the powers of 2 to the irrational, or 2 to the z times 3 to the z, one of them, something like this. You add a predicate naming this set. The theorem looks like this. It's not a simple theorem to state. So they call it a relative quantifier elimination. If they don't eliminate all quantifiers, they eliminate quantifiers down to something of a specific form. Never mind what the details are. This is sort of almost quantifier. Right? This psi is, let's say psi of x, y. Otherwise, that's nonsense. But it's sort of something quantifier free together with some stuff about this x, about u. That's allowed to have some quantifiers. First of all, despite being not quite a quantifier elimination result, that doesn't change anything. There are, again, lots of results in the literature that are these sort of not reducing things to no quantifiers, but reducing things to formulas of a special form. And the exact same properties of quantifier elimination apply, and the exact same methods work. They use a saturated embedding argument, otherwise I wouldn't be talking about it. So they show, in fact, more or less exactly this version we've been talking about. It turns out to be a much more complicated argument. in that the cases are a lot more subtle. So one of the cases is that A is in the distinguished group. And this case is sort of trivial because that's not true. Anyway, this case reduces to some stuff about the group U. The really messy case is the middle case, where essentially you have to pass, you pass to an elementary extension that could have other elements in it that come from this distinguished group, and then you look at the real closure of that. And so this is a much messier thing to deal with than just the, right, before we dealt with the algebraic closure of the domain of F, here we have this, well, there might be an extension of U, and then we take the closure together with the domain of F. So that's a much messier thing to talk about. And then the final case is the analog of being transcendental, but you're transcendental now over this much bigger thing, because you're transcendental over like the monster model of the U together. Furthermore, so unless you were really paying a lot of attention, you have no reason to think about this, but for algebraically closed fields, we actually never used the fact that M was algebraically closed. We used the fact that N was algebraically closed. But actually, we didn't use the fact that M was algebraically closed. Their proof is not like that. You actually need the domain to be real closed to guarantee that some things exist in it. So it's a much more complicated argument. And of course, the algorithm you get is more complicated. The point I just want to make is, nonetheless, this method of translating it into a statement about these approximations of models and playing this back and forth game where the models where these approximations try to force each other to be inconsistent really does work. So this statement about, so instead of enumerating statements like, right, so the algebraically closed fields, we enumerated these statements that were like, we're just that some sequence of polynomials was non-zero. And here we enumerate these much more complicated things where we say, well, there might be some elements satisfying this predicate, some elements in this special subgroup. And then there might be these additional things that are in their real closure. And if those happen, we satisfy, we are transcendental, we don't satisfy polynomials over these additional coefficients. But actually, once you find the right way to state that, and again, the model, you can really sort of look at the model theory and with some effort, read off from the model theory, right, what the right statement here is, you get a very analogous. So the analog of the transcendental step, you get something that looks like this, which is not pretty, but you do get an algorithm for computing this thing, right? Something that says, look, under the assumption that once I extend to, okay, these extra elements from the dense subgroup, plus some extra W's from the real closure, okay, then I get a quantifier-free equivalence. And if I'm not in this case, then there are finitely many disjuncts, and I can deal with each of those. And then I can reduce to the other cases, and one ultimately gets an algorithm that I'm obviously not going to go into further details about it the last 5 minutes. Okay, so the story here, right, the point I'm just trying to make is, first of all, there really is, like, we really can pretty consistently take statements about uncountable sets, and if they ought to provide an algorithm, if the thing we're using them for is to prove that computable functions are total, we really should be able to reinterpret them as being something about countable things. Often the price we pay for dealing with uncountability is having to push things up to these like dynamic higher order objects that do things back and forth instead of being just one stationary thing. And then once we've done that, this is exactly what proof binding is for, and proof binding gives us a systematic way to take, once we've translated things into a computable, into a countable setting, we can extract algorithms from them. And this works. Like, this is an actual practical implementable method. So I'm hoping this summer I'll finally get out the paper with sort of the first application of this to the boundaries, created results, and sometime after that, other things, just to sort of show that we can really do this and get new algorithms out of these smaller results.